Welcome back! In this lesson, we're going to look at a familiar mathematical concept in a new way, the inverse. So far in your math career, you've learned about several different types of inverses. There are additive and multiplicative inverses that we might use when solving equations, and there are inverses of functions, including exponential and trigonometric functions, that we've discussed in previous units in this course. Today, we're going to learn what it means for a matrix to have an inverse, how to tell if two matrices are inverses, and how to find the inverse of a matrix. The first question I'm wondering about is, why do matrices even need an inverse? How do we use it? The inverse of a matrix actually has a wide range of applications, including solving systems of equations, which we will do later in this unit. Reversing the action of a transformation, and converting between two coordinate systems. Inverse matrices are heavily applied in the field of robotics to direct kinetic motion and in cryptography to decode messages in cryptographic algorithms. Let's define what the inverse of a matrix actually is. For a square matrix A, the inverse of A is the matrix such that A times the inverse of A and the inverse of A times A both results in the identity matrix. Since we know matrix multiplication is not commutative, we have to test both directions to confirm that two matrices are inverses of each other. Recall from earlier in this unit that the identity matrix is a square matrix that has ones on the main diagonal and zeros in all other places. Before we get into the process of finding the inverse of a matrix, let's figure out how to tell if two matrices are inverses of each other. For this lesson, we will only be working with 2x2 matrices, though any square matrix may have a defined inverse matrix. We'll look into that more in Part 2. Consider matrices A and B. Determine whether A and B are inverses. Remember that the definition of the inverse of a matrix is that A times its inverse results in the identity matrix. In other words, A times B and B times A must equal the identity matrix. I know I can multiply these two matrices because the number of rows in B matches the number of columns in A. I also know that resulting matrix will be a 2x2 matrix. I'll start with A times B. A times B gives me 11 minus 10, negative 55 plus 55, 2 minus 2, and negative 10 plus 11, which simplifies to the identity matrix 1, 0, 0, 1. So far, so good. Now, pause the video and try B times A on your own. B times A gives us 11 minus 10, negative 5 plus 5, 22 minus 22, and negative 10 plus 11, which simplifies to 1, 0, 0, 1. Since both A times B and B times A results in the identity matrix, we can say that A and B are inverses of each other. Try this next example on your own. Pause the video and determine if C and D are inverses. Let's see how you did. I started with C times D, which gave me negative 4 plus 5, 1 plus 1, negative 20 minus 20, and 5 minus 4. This simplifies to 1, 2, negative 40, and 1. Is this the identity matrix? No, it's not. Even though we have ones on the diagonal, these other elements are not 0. What can we conclude from this? C and D are not inverses. It also means we don't have to bother with D times C since both directions must result in the identity matrix in order for two matrices to be inverses. Now that we know how to verify whether two matrices are inverses, let's figure out how to find the inverse of a 2 by 2 matrix. Just like with determinants, there is a handy shortcut for finding the inverse of a 2 by 2 matrix. You need two pieces of information to find the inverse of a 2 by 2 matrix: the determinant, which you learned how to calculate in the previous lesson, and the adjoint matrix. We're going to see the official definition of an adjoint matrix in the next lesson, but for today, we're all about the shortcuts. Let matrix M be the 2 by 2 matrix with elements A, B, C, and D, then the adjoint of matrix of M, denoted as ADJ parentheses M, is equal to D, negative B, negative C, A. So we have swapped the positions of A and D and flipped the signs of B and C. Let's practice this. Find the adjoint of matrix C. Start by swapping 1 and negative 4, and then flip the signs of 1 and 5, so the adjoint of C is negative 4, negative 1, negative 5, 1. Remember, we need the adjoint matrix and the determinant of C to find the inverse of C. Now that we have the adjoint matrix, let's find the determinant of C. Pause the video and find the determinant of C. The determinant of C is negative 4 minus 5, which equals negative 9. Now that we have both pieces of information, we can put this together to find the inverse of matrix C. The formula for the inverse of a matrix is the reciprocal of the determinant, or 1 over the determinant, times the adjoint matrix. We will simply plug in the values we found for each piece and solve with scalar multiplication. The reciprocal of the determinant is negative 1/9. Multiplying each element in the adjoint matrix by that value gives us the inverse of C, which is 4 over 9, 1 over 9, 5 over 9, and negative 1 over 9. Let's verify our work with matrix multiplication. When I multiply C times the inverse of C, we end up with the identity matrix. When I multiply the inverse of C times C, it also results in the identity matrix. So we correctly found the inverse of matrix C. Great job! Take a shot at this example on your own. Find the inverse of matrix K. Pause the video and come back to check your work. Let's review your work. First, I found the determinant of K, which gave me 18 minus negative 2, which is equal to 20. Then, I found the adjoint matrix by swapping 3 and 6 and flipping the signs of negative 2 and 1. Finally, I plugged the pieces into the formula to get 1 over 20 times the adjoint matrix. When I multiply, I get the inverse of K is 6 over 20, 2 over 20, negative 1 over 20, and 3 over 20. Is that what you had? Great! Let's take a look at one last example together. Find the inverse of matrix P. What are the two pieces we need to find the inverse? Right, the determinant and the adjoint matrix. First, I find the determinant, which is negative 12 minus negative 12, which equals 0. Next, we'll figure out the adjoint. Swap 2 and negative 6. Flip the signs of 3 and negative 4, so the adjoint is negative 6, negative 3, 4, and 2. Now we're ready to use the formula. 1 over the determinant, which is 0. Whoa, uh-oh, looks like we have a problem. Do you see the issue? We can't divide by 0. Dividing by 0 makes this undefined. This tells us that matrix P is what we call non-invertible, meaning it does not have an inverse. A non-invertible matrix, also called a singular matrix, is a matrix that does not have an inverse because its determinant is equal to 0. So when you're asked to find the inverse of a matrix, it's a good idea to start by calculating the determinant first. If it's equal to 0, you know the matrix doesn't have an inverse and you won't have to find its adjoint. Today, you learned how to verify whether two matrices are inverses by showing the product of the two matrices is equal to the identity matrix. You also learned the process for finding the inverse of a 2 by 2 matrix, which involves finding the determinant and adjoint matrix, then multiplying the adjoint matrix by the reciprocal of the determinant. You'll be using these skills in the next lesson, where we'll find the inverse of a 3 by 3 matrix. Be sure to complete the lesson activities before the online practice. This will help master these skills and help you in upcoming lessons for this unit. See you next time! Hey, hey.